Welcome everybody. We're going to have 3 lectures again on theory, but from a different aspect. So I'm not treating dynamics. I first look at electronic structure methods, and then in the afternoon we will more look into spin-orbit coupling and in how to calculate intersystem crossing rates from the ingredients that we have. We have started working on TADF only recently. I have long-standing experience in doing relativistic quantum chemistry. So intersystem crossing has been done by us a long time ago, and it was quite natural to move into this area, and I think it's very interesting. Now I have to switch that on. So here we will have electronic structure methods for excited states, and I will give you a brief overview. So it's very difficult to put everything into say just 45 minutes, and it might be that I run out of time, but in the afternoon sessions there's more time, so I can use this again. Let's start with molecular orbitals. Molecular orbitals are a real success, so to say, in chemistry, so the concept, because molecular orbital theory is a one-electron model. So you typically have, say, apart from spin, you have one electron sitting in the molecular orbital, and so this one particle nature makes it very easy to think, so to say, of excitations in terms of excitation of one electron from the ground state to the electronically excited state. So if we have, for instance, I have shown here a donor-acceptor molecule. In the donor we have dimethyl acridine, and the acceptor is a xanthone molecule, and we typically have here transitions, for example, from this highest occupied molecular orbital to the lowest unoccupied molecular orbital. And if you have these HOMO-LUMO transitions, you would call this a charge transfer state. And then you can have local excitations. For instance, if you have this non-bonding orbital on the oxygen of the xanthone to this pi orbital on the xanthone, and this you would call a locally excited state, because both orbitals are on the same subunit. So for thinking, this is a very good concept. For calculating excitation energies, we have to remember that molecular orbital energies are not observable. They cannot be measured, although you find this very often in literature that people have written, we have measured the HOMO energy, or we have measured the LUMO energy. What they mean is they have measured an ionization potential or an electron affinity, but they did not measure HOMO or LUMO energies. In particular, the excitation energy of the singlet, or also the excitation energy of the triplet, this is not the difference between HOMO and LUMO energy. This would be true in a one-particle model. So for the hydrogen atom, this is true. Also for the H2 plus molecule, this is true. But a donor-acceptor complex is not a one-electron system. And as soon as you have more, even in a 2-electron system, this is no longer true. So what we have to do is we can think in this molecular orbital picture, but when we do proper calculations, we will have to do something else. We will have to calculate the energy of the singlet state. We will have to calculate the energy of the triplet state. And then work with these energies, but please not only HOMO-LUMO energies. And what is even more important, I have very often found the case that even the first excited state does not come from HOMO-LUMO excitation. If you work with, for instance, polyacenes or polyenes, the first excited state is something completely else, has nothing to do with HOMO-LUMO energies. So please, this is what I would like to wish that you learn or take home as a take-home message. Please do not think that you can just calculate HOMO energies, LUMO energies, and you know something about the energy of the first excited state. Okay. In practical calculations, we need to consider electron correlation so that the electrons do not move independently. And we have a couple of wave function ab initio methods that can treat these electron correlations. And these ab initio methods have the advantage that they can be systematically improved. So we have, for instance, configuration interaction methods. I will tell you later what this is. For excited state, we need that in this multi-reference framework. We have perturbation theory that we can use on top of such a system. We have algebraic diagrammatic construction methods. This is more or less something like Malaplasset theory for the excited state. We have coupled cluster and so on and so on. The problem is, or the advantage is, these methods are very exact. The problem is they are so expensive, you can use them only for small molecules. So when you go to a typical donor-acceptor molecule, these methods are too expensive. You can nevertheless use them, so to say, to try and use them for benchmark methods, but you cannot use them. So we have to find more approximate methods that can deal with these systems and without, so to say, losing too much of the accuracy. So then we have, I put this in brackets here, in parentheses, because there are these methods like time-dependent Hartree-Fock and configuration interaction singles. I will even show you a quick glance what they are doing, but they are too inaccurate to be used. Then we have something, this is an approximation, so to say. You have these methods that you have truncated, multi-reference methods, and a method that I often use for benchmarking is these resolution of the identity linear response coupled cluster method, RICC2. I will not have the time to explain this to you, but I can recommend, for instance, if you are not sure whether the method you are going to use will describe your system properly, take the ground state, do a benchmark calculation at the ground state, and use something like RICC2 just to compare the energies that you have calculated and see whether the order of states you get is reasonable. Parametrized methods. So most of you probably have done some density functional calculations. This is the method that also people working with experiment typically use to describe their methods. The density functional method, of course, is a ground state method. So in order to get something for the excited state, you can treat, for instance, your triplet molecule with unrestricted density functional theory if you want. Linear response, time-dependent density functional methods is what most of you probably have done. before, and I will later on show you this method more in detail and also the pitfalls that this method bears. And you can have an approximation of that. The method that we are typically using is a combination of density functional theory and a wave function-based method, namely the method which is named DFT-MRCI. And I will also show you examples how this can be used and what the idea behind this method is. And then we have, of course, semi-empirical wave functions methods. They are much, much faster, of course, than the other quantum chemical methods, but they have to be really benchmarked strongly. What you should never do, never ever, is mix different methods to compare energies with. So you should never, there is one daunting example, and I took that from a recent science publication. You should never use, so to say, what these authors did. They used time-dependent density functional theory to calculate a singlet state. So this is a gold complex here in this case, where you have the transition, the HOMO is localized on a ligand, and the LUMO is more or less localized on the metal and some also on the ligand. So what you have here essentially is a ligand to metal charge transfer, not a metal to ligand charge transfer, but a ligand to metal charge transfer state. And the authors calculated the S1 with time-dependent density functional theory and the T1 energy with unrestricted density functional theory, and then postulated a new mechanism which they called rotationally assessed spin state inversion mechanism, so that the singlet dives below the triplet when you start rotating here the ligands. If you do a calculation where you just use time-dependent density functional theory, so a consistent picture. I do not say that time-dependent density functional theory is correct. I just say if you use it consistently, what you then get is a triplet state that is always below the singlet state. So in this case, you may get to strange conclusions if you think you can use the triplets, the unrestricted DFT for triplets and the time-dependent DFT for singlet. So, my warning, never mix singlet and triplet energies from different theory levels. As I said, density functional theory is what most of you will use or will have been using so far. And I will explain in a nutshell what density functional theory method is. And then we see what the problems of density functional theory is. So density functional theory is just an energy functional that depends on the density. So this rho here is the electronic density. It's essentially a ground state energy method, as I said. So why should we bother about it? We cannot understand time-dependent density functional theory if we do not use, if we do not know DFT, and we need the molecular orbitals from density functional theory as a starting for time-dependent density. So, there are the famous Hohenberg-Kohn theorems, and they say there is a one-to-one correspondence between the potential, the external potential, and the density of the functional, which means I can express so to say, the functional here as an integral over this density and this external potential. And then I have as a further ingredient the kinetic energy and the electron-electron interaction energy as a function of the density. There is also a variation theory for this density functional. So this means that if I have a test density, then the energy of this test density is always larger than the energy of the true density. And for this reason, we can vary, so to say, our density and then look for the lowest point that we find, and this is then the approximation that we need. The problem is that we do not know this functional. We do not know the functional dependence of the density. So therefore, we have to find approximations how we, as Tom said this morning, quantum chemistry is finding approximations, and in this case, we try to find an expression in particular for the kinetic energy and for the electron-electron interaction energy. And there comes in the approximation of Kohn and Sham. They said that they defined some fictitious system, namely a system where we again have orbitals, and they use these Kohn-Sham orbitals to find the kinetic energy functional and also to define the density. So we again solve, so to say, have an orbital picture. Like in Hartree-Fock theory, we have one Slater determinant in this case, and from this Slater determinant then we can find the kinetic energy and the density. And going through this, we require, so to say, that this fictitious system has the same density as our true system. And then we have here the, so to say, the energy. And we return to our proper system, and then we have here these approximations. We have the Coulomb energy in this system, which is just the integral over the two densities defined by the distance between the two electrons. And then everything that we do not know exactly is put into this last term, which is the so-called exchange correlation energy functional. So in particular, it contains corrections to the kinetic energy, and it contains corrections for the electron-electron interaction, because you know electrons carry spins. And in your Coulomb interaction, you do not take care of the spin of the particle. And even if you do not have a spin-dependent Hamiltonian, spin plays a role, because Pauli principle tells you that you cannot, when you interchange the places of two electrons, then your wave function changes, so to say, the sign, and you will never have two electrons with equal spin at the same place in space. So, and therefore, you have to correct your electron-electron interaction for not only Coulomb interaction, but this correction is put into this exchange Coulomb, in this exchange correlation functional. When you then use a basis set, you get a set of equations. These are the Kohn-Sham equations for the orbitals, where you have here the kinetic energy, the interaction with the nuclei. Here we have the Coulomb interaction, and here we have this exchange correlation potential. And as I said, you do, like for Hartree-Fock, you choose a basis set, put that into that, optimize the coefficients, and then these are the Kohn-Sham equations for this system. This potential here is a local and multiplicative potential if you use just rho and the gradients here to express your exchange correlation functional. And this is what causes the problem when you then go to excited state density. So I also put you the corresponding expression for Hartree-Fock. In Hartree-Fock theory, all these terms here are identical. And the only thing that changes, you do not have correlation in Hartree-Fock theory, but your potential here is, this is the exchange potential, where you also have, you see, it's an electron-electron interaction, but this term here, this P R prime, this exchanges the coordinates of your particle. And this expression, so to say, is non-multiplicative, and it's really an exchange interaction. Then you can, people have then thought of mixing, so to say, elements of density functional theory and wave function theory, because it turned out that pure density functionals do not really properly describe molecular systems. They are very good for solid states, for describing metallic systems, things like that, but they are not well suited for molecules. And therefore, people started mixing, so to say, density functional theory and Hartree-Fock. And I think the first person doing that was Axel Becker. And he, in this Becker half and half, he just chose a parameter A and said, I express my exchange energy as a sum of a density functional exchange and a Hartree-Fock exchange, and this parameter A was chosen in this case to be 0.5. And there are very many, and I only show you the most used, I think in chemistry, the most used density functional people use is B3LYP. And this is a functional that contains density functional exchange and Hartree-Fock exchange, and it does also some mixing here in the correlation part. And these parameters A, B, and C were fitted to atomization energies and other experimental data. And this brings me to say that most of the density functionals are not ab initio theories, but they contain some parameters that have been taken from experiment. Good or not good? This was just a quick view through density functional theory. So how do we get from this? Now we have orbitals, we have orbital energies. We know approximately what the exchange correlation potential is. How do we get to electronically excited states? We get to electronically excited states if we do something very similar like experiment. I will not show you here a step-by-step derivation. If you are interested in that, you can just look it up in this article by Prof and Head Gordon. what we do, more or less, is we let the molecule interact with an oscillating perturbation. It's like shining light on a molecule. There you also have an oscillating electromagnetic field that takes the molecule from the ground state to the excited state. And in time-dependent perturbation theory, you do something similar. And this is, so to say, the perturbation that you apply. And so what do you get in experiment? You get nothing, nothing, nothing. And then if you come with your energy or with your pulse close to the excited state energy, you get some resonance. And so you get some excitation. And here it's more or less the same, although the resonances are treated a little bit different. So this omega is our excitation frequency, and the idea is to find an omega such that the perturbation is in resonance with the energy of the excited state. And this perturbation, if you apply that to the density matrix, you generate, so to say, this is the density matrix of the unperturbed system. You have also then a perturbed density. And you got also a perturbation in the Fock matrix here. This is the unperturbed Fock matrix. You add the perturbation H prime to this Fock matrix, and because the Fock matrix itself depends on the density, you also get a perturbation here through the change in the density matrix. And after, so this change in the Fock matrix has more or less two terms, and we need to understand the nomenclature here. So this is a two-electron integral in the so-called Mulliken notation, and the Mulliken notation is a two-electron integral here, and the indices here tell you this is electron 1, which corresponds to these two terms, and these two have electron 2, or the primed indices here. And the omega here just stands for this expression, and this is the integral over the exchange correlation functional. So here you have the functional derivatives of this exchange correlation energy with respect to the density of particle r and the density of particle r prime. So when we now assume that these transitions occur with a small perturbation, and then you have to do a lot of algebra, you end up then with these kinds of equations. These are the time-dependent density functional equations. These are non-Hermitian equations. Don't mind about that. So you solve this equation for the omega, and the omega is our, so to say, time-dependent DFT energy. It's important to notice here that these two types of integrals, which I just introduced, this is a normal Coulomb integral, and this is an exchange type integral for the in the DFT theory. They are here in this matrix A, and in B we have similar integrals. So when you solve this equation, we obtain these TD-DFT excitation energies omega. And we can do something very similar for time-dependent Hartree-Fock. I said time-dependent Hartree-Fock is not really usable, but I need it here to explain the problems of TD-DFT. So time-dependent Hartree-Fock has exactly the same expression with one exception. So I showed you that the exchange energy is different, formulated in Hartree-Fock. Here we have terms AI, omega, JB, and in time-dependent Hartree-Fock, the indices here have changed. This is a proper exchange integral in time-dependent Hartree-Fock. So, an example taken from the work of Prof and Gordon. So, assume you have here molecular orbitals in the electronic ground state, which are termed I and J, and the unoccupied orbitals, the valence state, are termed A and B, and you have two systems, system 1 and system 2. So in the top we have a valence excited state, so we take an electron out of orbital I on the same system and put it in an unoccupied orbital A on the same subsystem. This is called a valence excited state. And in the bottom we have a charge transfer state. So we take an electron out of orbital I and put it here in a molecular orbital on system 2. This is a charge transfer state. And when they are far apart, these two subsystems, then we do not have an overlap of molecular orbital densities when going from I to A. And this results in a lot of artifacts in TDDFT energy. So this is the example of a porphyrin, or porphyrin derivative. This is actually something else. Chlorine and zinc chlorine coupled here by some spacer. And what do you see here? The highest molecular orbital is on the chlorine. The highest the highest molecular orbital is on the zinc chlorine. The highest unoccupied, the LUMO, is on the chlorine itself. And what you see here are the experimental energies here in this line. And you see that the lowest experimental states are all locally excited states. So local excitation either on the zinc bacterial chlorine or on the bacterial chlorine, and charge transfer excitations are rather high up in energy. What you get if you use a density functional, here this has no, this is not a hybrid functional, but it's just a local density functional. You see that you get the first four states here are all charge transfer states, and these charge transfer states is just an artifact of the method. So they are not present here. Experiment tells us the lowest excited states are locally excited states. So what is the reason? The excitation energies are much too low, and also we have the low, a wrong long-range behavior. If we take these two molecules, so to say we have a ethylene and a tetrafluoroethylene, we expect that the tetrafluoroethylene is it takes electrons, so and ethylene is the donor, the tetrafluoroethylene is the acceptor, and then if we have a charge transfer from ethylene to tetrafluoroethylene and take these molecules apart, you would expect a 1/R behavior of the two systems, because you have a positive charge here, a negative charge here. The Coulomb interaction is 1/R. So this is what you expect if you take these systems apart. This is what you see in CI singles, or time-dependent Hartree-Fock. In the local density functionals, you see essentially a flat line. So if your donor and your acceptor are far apart, you see that the charge transfer states are much, much, much too low. And this is the problem. So what is the origin, so to say? If you do time-dependent Hartree-Fock, what do you get? You get an excitation from I here to A. So we have to look at this excitation, have these integrals here, and what we get essentially is a difference of the orbital energies plus or minus in this case an additional 2-electron integral, which in this case here describes, so to say, the interaction of the whole and the particle. The most decisive element is the diagonal element. So if we look at the system at this integral, so we see we have here the orbital energy, so to say, of A, the orbital energy of the electron affinity of B, and we have an integral where we have the interaction of the charge density of particle I and the charge density of particle A. And for this reason, we get the correct long-range behavior because we have these two systems with the 1/r dependence. If we do the same for time-dependent DFT, we have, so to say, here, these terms are now not proper exchange integrals, but we have this W here. And then, if you look at the diagonal terms, what you see is that A and I are on different systems. So the overlap between A and I is 0, and for this reason, this integral here is 0. It was not 0 in Hartree-Fock theory because there you exchange, so to say, the particles, and then you have something left. So this exchange integral is missing, and therefore you get only the difference of the orbital energies, and this Coulomb term is missing, and therefore you get this flat line. So you get a wrong long-range behavior. So you say, okay, Hartree-Fock energy or Hartree-Fock contributions can change this. Yes, they do. You can add these hybrid functionals, of course. So you do not have only this type of exchange. You also have Hartree-Fock exchange, and here you can see it very nicely. The order of these orbitals is different from the order of here. So here we have orbitals on two different subsystems for particle 1, and here the orbitals for particle 1 are on the same subsystem. Here we have AI, and in the other one we have JIAB. That is true, but if we look at this dependence, you see you can correct only slightly. Becker half and half has 50%, so you get 50% of your 1/r dependence here. And this one. And if you have this Becker 3 LYP, you get only 20%, so you get not completely flat line, but still your orbital energies are too low. Now let me come to an example which is here for a TADF emitter. This is the acridine xanthone complex I have shown you right in the beginning. And here we have a case where the potential energies are very mixed. So what we have here, we have two charge transfer states. This the singlet and the triplet. So the red curve are the charge transfer states. Full line is the singlet, and the open lines, so the dotted lines, are the triplet or the open symbols are the triplets. And you see that there are other states coming down in energy, and in this case, the example differs from what Tom has been telling you, because these states that come down, in particular the green ones, the green singlet here, the green singlet has the same symmetry as the charge transfer. So this coordinate is essentially a CO stretch. So this is a totally symmetric mode which can, so to say, mix charge transfer and n pi star character. And in addition, it turns out that for the spin orbit, for the vibronic spin orbit coupling, this blue state, which is a pi star state, also plays an essential role. So we have 5 states here that interact in this system. And you can imagine, if you want to get, so to say, the dynamics right in this system, you have to describe these states, or you get the energy difference between these states properly. And what I show you now is, I have not presented the DFT-MRCI method yet. I will do this afternoon, probably because we're running out of time. And I have compared this to RICC2. This is an ab initio method, a coupled cluster method, an approximate one, but we can be sure that in this case the order of states is approximately correct. And we see from these RICC2 calculations that yes, the charge transfer states are lowest in energies. Then we have a bunch of locally excited states above. This is just the ground state minimum, but you see the order of states is fine. The DFT-MRCI method is a combination of density functional theory and multi-reference CI method. They also give you the charge transfer states as the lowest states. There are 3 triplet states here close by. They are in slightly different order, but essentially you reproduce here the order of states in this DFT-MRCI method. And this CC2 method does not have multi-configuration effects, does not take into account double excitation. So it turns out actually that with regard to experiments, the DFT-MRCI is a bit better than CC2, but the order of states is more or less preserved. Now look what happens in time-dependent DFT for this molecule using the Becker 3 LYP functional, which is the standard functional people are using also for TADF emitters. First of all, you see that the valence states, so the locally excited states, are well described. So they are essentially correct here in energy. But you also see that the gap between the valence excited state and the charge transfer state has become very large. So the charge transfer state is way too low in energy compared to this scheme. So if you use TDDFT, you will never see any crossing between the charge transfer state and the locally excited state. And moreover, there are further charge transfer states coming down in energy that lie here in between. Well, what could one do? There is a possibility. The problem is in the long-range behavior because we have charge transfer. These 2 parts are, so to say, spatially apart. We could try and find having some correct or more correct long-range behavior, and we know that CI singles does a better job for the long-range behavior. We also know that TDDFT performs much better for correlation energy for the locally excited states. So the idea was, and this was not my idea, but other people's idea, to mix these approaches and have the short-range part by density functional theory and treat the long-range part by wave function methods. And the idea was therefore to split up, so to say, the Coulomb, the interaction, the 1 over R2, into a short-range part and a long-range part. And I quickly switch to the next page, so to say, to show you the error function. This error function is 0 at 0 distance, and then it quickly grows to go to 1. And going back, then we see that this 1 minus this error function, this gives you the short range, because at long range, the error function cancels the 1, and the other one is the long range part. I'm quickly done. I need 2 more minutes. What happens if we use such long-range corrected functionals now for our complex? So the charge transfer states are shifted up in energies, as they should, but they are shifted up a little bit too much, and locally excited triplet states are stabilized. This is the Chem B3 lib functional. There are other functionals like this WB96XD. I just chose a few functionals that are implemented in Gaussian. And what you see is, again, the charge transfer states are indeed shifted upwards, but to an energy, so this is completely wrong, what you get out of here. And it's even worse in this WPBE, where the charge transfer triplet is the the 10th triplet state at all. So this is not the concept to calculate electronically excited energies for TADF emitters. And so concluding this part, we see this RICC2 finds only one low-lying pair of charge transfer states. And the spectrum itself is a bit blue shifted. The DFT-MRCI, which I have not introduced, finds essentially the same order, and the spectrum is a good agreement with experimentally known data. All the functionals, so if you use standard functional like Beck 3 Li-Yang par, well describes the locally excited valence states, but it fails on the charge transfer states. Whoops. And these long-range corrected functionals, they overcorrect the charge transfer states. And they furthermore produce problems with the locally excited triplet states, which are all too low for these organic donor-acceptor systems. And so to say, in the second part of this lecture, which will then be shifted to my first afternoon lecture, I will show you or introduce another approach how to correct, so to say, these wrong density functional theory to get a valence treatment of locally excited state and of valence excited